The objective of this lab is to measure the impedances of test instruments. To do so, we're first going to measure the internal resistance of a VOM. Second, we're going to measure the internal resistance and impedance of a scope. Third, we're going to model the scope as a resistor parallel with a capacitor. In part 1, to measure the internal resistance of a VOM, also known as a volt-ohm milliammeter, you're going to first need a 1 megaohm resistor, second, a breadboard, third, a VOM, and finally, a voltage source. Connect the reading end of your VOM in series with your 1 megaohm resistor. Set the reading of your VOM to a 20 volt reading range, and input a 5 volt voltage into your circuit. You should see a reading of about 4.54 volts on your VOM. Again, we can model this circuit as a 1 megaohm resistor in series with the resistance of the VOM. To find the internal resistance of the VOM, we can use a voltage divider equation, and we get that it is 9.87 megaohms. In part 2, to measure the internal resistance and impedance of a scope, you're going to need 1 megaohm resistor, 1 breadboard, 1 function generator, and finally, 1 scope. To measure the internal resistance of the scope, we're first going to put a 100 Hz sine wave into the input of the circuit. Then we're going to use the probe to read the value of the voltage outputted before we connect the resistor. As you can see, without the resistor connected, the sine wave has a 5 volt peak-to-peak amplitude. Now we're going to switch the probe over to be in series with the resistor. When we do that, this is the circuit as follows, and our peak-to-peak amplitude on the sine wave changes to about 2.33 volts. Now we model the scope as a resistor in parallel with a capacitor. In the frequency range we're operating in now, which is about 100 Hz, the capacitor has a very high input impedance, which means it acts as an open circuit and therefore can be ignored. So the circuit reduces to a 1 megaohm resistor in series with the resistance of the scope. We can again use the voltage divider equation to find the internal resistance of the scope. To measure the internal impedance of the scope, we will use this figure, L3.9, to set up our circuit. First, when we input a low frequency 100 Hz sine wave into our circuit, we get an output of 2.4 volts after the resistor and 5 volts before the resistor. Next, we are going to increase our input frequency to be about 10 kilohertz. Now, as you can see on the scope, there is a much higher voltage attenuation. At this higher frequency, the C scope now comes into play. To find what C scope is, we must first find the impedance of each branch. The impedance of the first branch, Z1, is found as shown. Impedance of the second branch, Z2, is found as shown. Now, using our knowledge of circuits and the results we acquired from the graphs, we can plug numbers in to find that the C scope is approximately 11 picofarads.